Yeah, I think so.
Can you confirm that you can hear us online?
Yeah, I think so. Yes.
Yeah.
Okay.
Maybe if you want to increase the volume for
the what?
The questions afterwards, if you want to increase the volume.
Yeah, I think it's quite high, yeah. Because yeah. Good. Okay. You wanna go first?
Yeah. I'm the one introducing them.
Yeah.
Okay, hello everyone. So thank you for being here today. So today we're going to have a presentation by Lluís that is under the Severo Ochoa seminars. So Lluís is a PhD student at the Earth Science Department under the supervision of Marcos Donat and Albert Soret. So his work is focusing on applying machine learning to improve the understanding of prediction and interannual climate variability, with particular expertise in subseasonal to seasonal forecasting. And today he's going to be talking to us about his work that he's been developing during his PhD, and also the work that he developed during his stay in Leipzig University with under the Severo program. So the floor is yours.
Yeah. So yeah, thank you, Amanda, for the nice introduction. Yeah, just to say that this work is conducted on in the context of my PhD, but there are also several people from the from BSc and ex-BSc already involved that you see listed here. Okay, so I think, well, the motivation of my whole PhD on applying machine learning to seasonal climate prediction might be quite obvious to some of you. So we have seen like a very recent explosion of works applying machine learning for weather prediction, and these different works that we have seen from the private sector and different public institutions claim like very good levels of skill at predicting the weather time scale. And basically, well, machine learning is offering this capability to model very complex nonlinear relationships at a fraction of the computational cost. And this is very important for the climate and the weather community in this case, because we are using a lot of HPC resources to create the simulations that predict the weather and climate system. So with this huge revolution happening on the weather prediction, of course, we also wanted to take a look at climate predictions. Yet we have to be a bit careful because, yeah, we have seen a lot of papers from Nature and so on that claim the importance or the success of these models at replicating what traditional dynamical models do. But we also see a lot of literature pointing at some issues from these weather models, and I leave some examples here. And this could be from physical inconsistencies in reproducing cyclones, or lack of intensity in out of distribution predictions, and so on, which is quite interesting. And that's why, if you know, maybe you noticed before, but I put like a question mark in whether this is a success or not. So my opinion is like we are still trying to understand how powerful these models are, and yeah, and which are the possible benefits, but also the weaknesses of these models. But in my case, I'm not going to talk about weather. I'm focused on the seasonal time scale. I see so many people here from like probably knows already what seasonal prediction is, but for the people that might not know, here instead of covering the weather time scale, so what is going to happen the next week or the next 2 weeks, we'll try to predict anomalies of the climate system one season ahead on time. So basically, one example could be we are now almost in October and we want to know how the next winter is going to be. So this could be a prediction. It's going to be warmer than normal. It's going to be below normal, so it's going to be colder. We will have more rain or less. So this is what we are trying to cover in this time scale. Some people maybe, for sure some of you know, but some other people might not know. The atmosphere has like a predictability limit of 2 weeks. So from 2 weeks onwards, the atmosphere is a completely chaotic system and there is no memory in the system. So how it is that we can predict anomalies one season ahead? And the basic idea is that in the climate system, we have other components. So luckily, so we have also the oceans, we have the land surface, we have the ice sheets and so on. And these components have, some of them, lower evolutions compared to the atmosphere and can force the atmosphere, so can change the behavior of the atmosphere. To what degree these components affect the atmosphere can give us some windows of opportunities to predict the seasonal timescale. So the big picture that you have to get here is that we have a very chaotic system in the middle that interplays with slow varying, more predictable components. So at the end, we have like a chaotic system with some degrees of predictability, and this will become important later. So when I'm trying to apply machine learning for the climate or seasonal timescale, we have a big bottleneck, and it's mainly the lack of samples, available samples compared to weather timescale. And to illustrate this, so we have 40, 50, 60 years of observational data, depends on the sources that we get. 40 if we use satellite observations. We have this data available at very high frequency input, so we have this data available even at 1 hourly, 6 hourly frequency. So one might think that we have a lot of data to train these large deep learning models, but this is not the case for seasonal predictions. The problem here is that the processes we are trying to predict, they have this very slow varying nature. They can take years or seasons to happen or to oscillate from one state to another. And if we want to like learn the relationship between these different states and the final predictions, we need a lot of examples of these different situations happening. So at the end, what happens is that for the seasonal timescale, almost 1 year becomes one sample. So at the end, we have like 50, 60 samples in our data set, and to train like a huge deep learning algorithm, this is super problematic because usually these algorithms have millions of parameters that they need to fit, and usually you need at least a data set that is only on the order of thousands of samples at least. So to tackle this problem, we see like two main research lines. So the first one is approaches where you try to train your deep learning algorithm on climate model simulations. So instead of using direct observations, you try to go to climate simulations like CMIP, which are like projection simulations, or other types of simulations, and then you make this model learn to predict the seasonal timescale within this climate simulation. This is one side. Here, because we have many simulations, we can create as many as we want, and we have scenarios and historical simulations. We can create datasets that are on the order of thousands of samples, and then start to train some deep learning models. The other research line, which is very recent, like from the last year or two, is to use these weather emulators that I showed before to do longer timescale simulations, so to do longer simulations. And just try to predict the climate with these models. The problem is that these weather models are usually not stable at longer simulation runs. And then, so people is trying to enforce physical constraints or maybe define like different hybrid approaches to stabilize these models and be able to do these long simulations. Yet, these two approaches take like very big assumptions. So the first one, on the first side, when you use a climate simulations to train a machine learning model, you assume that the climate model is reproducing all the processes that you want to capture properly. And we know, many of us here, that this is not the case for many of the processes. On the other side, what the people using weather emulators to do longer runs are assuming is like to predict the climate with all the different variations that climate might have across years and decades and so on. Just learning at the weather time scale on 40 years of data is enough. So everything that has happened at that weather time scale in these 40 years of data will be enough to extrapolate to the future. And this is a huge also assumption because like the machine learning models are very sensitive to out of distribution setups. So we'll see what happens in the next years. But for my work, I'm taking the first assumption. So we train our models on climate simulations, and I will explain a bit later more. So yeah, the objective of the work I will show today is to do like this kind of seasonal predictions. So we will try to predict in the what we call lead times 1 to 3. So this means that, for example, if we're using information up to the 1st of November, we target the DGF or the December, January, February season. So we skip the whole November and then we start predicting. And here what we are doing is like we predict the whole seasonal anomaly. So it's like the 3 months anomaly, so the conditions for the whole period. And for the inputs, we use information monthly monthly means from different variables that you see listed here, like temperature, precipitation, and so on, for the preceding 6 months. So basically, the whole thing is to predict with this setup, use a probabilistic model. We really focus on the probabilistic side because, as I mentioned, the climate system is very chaotic because we have the atmosphere adding a lot of stochasticity there and many other sources of uncertainty that I will not mention. But so to build a probabilistic model, we will target a global prediction, so the whole global average, and for the whole globe, and for different essential climate variables. In this case, it's going to be temperature, precipitation, and other variables. And then on this lead time that I mentioned, we used climate model output to train it. So here you see the table of the summary of the models that we use. We use large ensembles from CMIP6. So we have different large ensembles, and basically the setup is the following. We train using the CMIP6 simulations, validate our models to know which is the best one using these CMIP6 simulations, and then we tested everything on a real world setup using ERA 5 observations. So once the model has been trained on these simulations, how good is it on the observations? And then what I will show today is like we focus on trying to assess its performance, so against the climatological forecast. This basically in seasonal forecasting means that we predict what normally happens. So what normally happens is what is gonna happen next season, and this is a kind of a powerful benchmark at the seasonal timescale. Then we assess the performance against System 5, which is the dynamical model from the ESMWF. So it's like the state-of-the-art dynamical model for seasonal predictions. And then we try to do all this in a context of climate change. So we have climate change inducing trends in different variables like temperature and so on. And these trends can provide us like spurious estimates of skills. So basically, we could be fooled by thinking that our model that just predicts the evolution of climate change, so a simple trend, is skillful enough. But we are really not focusing, and we really don't want this information. What we want is to predict the changes from year to year beyond this trend, and this is very important to take into account in the verification. And then I will show some work on trying to understand why the model is skillful and the teleconnections and so on. Yeah. Okay, so to build, I'm gonna do a short introduction on how the type of models or the generative models that I use work. Basically, they are probabilistic model, and in essence, what we are trying to do is to create a model that learns the distribution of our data. So basically, we are not trying to build a model that learns like a deterministic function and so on. It is completely focused on learning the distribution. So basically, you use some training data, create your fake distribution, and then you just generate new data with this new distribution that the model has learned, and you just compare what you obtain against observations. Ideally, you would like to have high probabilities for the testing data that you observe in your learned distribution. So meaning that you have managed to learn something that is close to what the distribution from which the data comes from. This is basically what all generative models do. So basically what ChatGPT would say, or even like DALI and this kind of generative image models do, but on the mathematical side. And there are a big flavor of different generative models. In this work, I'm gonna center myself on variation autoencoders, and basically the motivation to use this type of model was because there was this paper published by Pan et al. On 2022, which was one of the first applications of generative modeling for seasonal predictions, and we wanted to learn a bit more from this. Still, there are many models that are now very interesting, and they provide better modeling, but for our first work this was our main objective, to use this type of model. There is a whole mathematical framework of why variation autoencoders are the way they are. I think I'm gonna skip this for this talk probably. If you're interested, I can explain to you more into detail, but it's something that takes some time to digest. The only thing that maybe it's worth mentioning is that the loss function is like a mix of two terms. One is a reconstruction term. Basically, it tells you if the samples that you generate are similar to the ones that we observe. This is quite easy. And then there is a regularizer term that I'm not going to enter into detail, but basically it makes the whole thing a bit more compliant. And the issue here is that, and I think it's the main issue of variation autoencoders is like, because they have these constructing terms, they are kind of difficult to train. And yeah, this is something problematic of this type of models. This is something we are looking in the future with trying to tackle in the future with other architectures. Okay, but if we focus now on our approach, what we do for the target variable in order to account for the trends, climate change trends that I mentioned before, we do a target decomposition on the target variable. So basically, we decompose our variable into two components. The first one is the trend. So it's a trend imposed by climate change or forcings in general. And the other one is the interannual variability. So basically, in yellow, we have what we really want to predict. And in red, what we have the evolution of climate change from one year to another. It's more or less simple. So basically, our model will focus on predicting the difficult part, the interannual variability. And then the second part, the trend, is handled by a very simple nonlinear regression that gives you what is the component from the trend, well, the add-on from the trend from year to year. And then here we have the whole machinery of the variation autoencoder. Basically, because of the mathematical framework that I showed you earlier, the variation autoencoder has three main parts. So first, there is an encoding from the input. So basically, it takes the input information and condenses this information into some latent variables. It's like some meaningful dimensions that have contained all the information. Is something very similar to what we do with PCA in climate science. So basically, we obtain pieces that are informative, but here is done in a more nonlinear and a bit more free way. To do this, we use vision transformers, which is like an architecture that has been widely used in the computer vision and large language models community. And we use this kind of architecture instead of another thing like a convolutional network because we want to extract information from very distant places in the world that might be connected remotely. And for these kind of applications, vision transformers can be more helpful. Then we have also an encoding for the target variable. This is only used on the training of the model, and it's for the optimization in order to obtain a meaningful distribution here. And when you create the predictions, this whole transformer for the target variable is removed. And then we have the decoder. So basically, the inputs go into the input encoder, get combined with the length distribution, which lies here in this set variable, which is basically a parameterized multidimensional Gaussian. And all this is combined in order to generate a new prediction, this kind of decoder, the CNN. I know it might be everything a bit confusing, but basically, what we get from using these kind of models that are probabilistic and not other type of model is the capability of doing some ensemble prediction. So basically, once we have learned this distribution here, we can sample from it and combine this with the input variables to generate new ensembles. So basically, if you see here in this plot, this is just an illustration of what happens as we increase the ensemble size for a temperature prediction in a random point. In blue, you see one ensemble, it's blue in this case, the first time series, and in red, you see the observation. And here you see the ACC, which is just the correlation between the observation and our prediction. As we increase the ensemble size, we see the individual ensembles in thinner blue and the ensemble median in thick blue. We extract like the predictable signal, and you can see how the ACC slowly converges to a higher value. And then we can sample as many members as we want from this type of model in a very cheap way. So, and this is the good benefit compared to dynamical models. So this is a whole data workflow in Manner 5, but basically the important information here is like training all this model for doing global prediction and even doing 150 members. Like all this training takes like 1.5 hours in a single node of Manner 5 using 4 GPUs. But then once it's trained, like the inference is very fast. Like in seconds, you can generate as many ensembles as you want, and this is quite interesting. Okay. So results. First, like a very quick qualitative assessment against System 5. So in the rows in second and fourth row, you see the System 5, so our state-of-the-art benchmark. And we see temperature and precipitation predictions. And on the first and third row, we see our predictions. And in every column, you can see the different seasons. And you can see in terms of correlation, so this is just the anomaly correlation coefficient for this period here. We see that the patterns are quite aligned and quite similar to System 5. So at least from the first side, without the trending or doing anything to the data, we get very similar performance. And also, if you see the patterns of rainfall for the different seasons, they are quite similar. And this is quite interesting because we are training a deep learning model on climate projections from CMIP6 that they don't have anything to do with seasonal. And then we are doing like an initialized prediction with only this information. And this is AI5 observation, so this real performance in a sense. Yet this assessment is very simple. So I've been at BSc 7 years, and verification of predictions is the most difficult thing ever. Like every year I learn more about verification. I know how complex it is, and there's no straightforward. So yeah, like staying in this setup is like very simplistic, and it might give you a good overview of performance, but we need more metrics to assess how good the models are from the statistical point of view. And for this here in our work, we use skill scores. So we are using 2 skill scores, the root mean square error skill score. So basically the difference against the reference or the benchmark. In this case here is the climatology, and the CRPS skill score, which is also, it's like a probabilistic measure of performance. So in one, we compare distributions, in the other one is just an ensemble mean. And this is for temperature, and as I said, compare against the climatological forecast. So when you see bluish colors, it means that we are better than predicting that what happened in the past is going to happen in the future. And when you see reddish, is that we don't even reach this benchmark. And if you notice there, we are detrending this temperature prediction. So here there is no influence of trends, meaning that all this skill that we are gaining is beyond the one that we could obtain by just predicting the trend, which is normally a lot. And we did exactly the same against System 5. So it's like same plot, but now against System 5. And here, of course, System 5 is a harder benchmark to beat. So of course we get like lower skill levels, but still for us, it was kind of a surprise that we could manage to be better than System 5 in some parts of the world. Which is interesting because System 5 is this dynamical model that has to be initialized once a month, and it takes a whole supercomputer and so on. And yeah, this is more or less what I mentioned. And more or less like the picture is very similar across seasons. So of course, higher skill values against the climatology, and then against System 5, yeah, it's more scattered, but still we get some degree of predictability. Of improvement, sorry. We did the same against precipitation. So precipitation and rainfall is a much harder benchmark in general for all the systems. I think you have also seen it here. If you compare System 5 has way more predictability for temperature than precipitation. And then, so basically we did the same thing, and against the climatology, yeah, we get more or less similar skill, skill in areas that I think some people here will think that makes sense. And then against System 5, we don't get much much improvement against System 5. we get in some places some statistical improvements, although we have to say that System 5 is really outperforming on the equatorial band, and outside this band is like comparing to very noisy forecasts, we could say. Yeah, and then this is the same for all the seasons and so on. So we mainly motivated because we were getting some degrees of predictability, and we had many people asking us, okay, is this pure noise or where is this still coming from? We started to do some analysis on how these kind of models were learning classic teleconnections that we know. So basically, teleconnections, for the one that might not know, are these important processes that happen in the climate system that link anomalies in some places of the globe to very distant places. For seasonal prediction, a big source of teleconnections, or even like a big mode of variability is ENSO in the Pacific. So here we tested how ENSO was reproduced by our model compared to observations from ERA 5 and to System 5. So basically we do a regression of the predicted ENSO index against the temperature, the predicted temperature and precipitation fields. So basically, if these two are in line with what we get in observations, we could say that we are reproducing a more or less realistic ENSO pattern. And then we compare this against System 5. And what we see is quite interesting. So for instance, on a first qualitative point of view, we could say that we get something that resembles what we see in observations, but there are many details we need to focus on. So for precipitation also in the whole Pacific, even entering in the Indian Ocean, we get like a quite good response from rainfall to our own ENSO index if we compare this against ERA 5. And even it seems like a more clear signal if we compare it against System 5 that seems to overall have like this weaker response to its own ENSO. And for temperature, it's kind of the same thing. We see an over response compared to System 5, but also we see some like low negative anticorrelations there that probably indicate that there are some biases that for sure that we are learning from these CMIP6 simulations that project into these predictions. We did a similar analysis with the North Atlantic oscillation in Europe. So it's basically also another important mode of variability, but this case for the North Atlantic sector. And we see again that our model manages to get a response that seems to be quite in line with what we get what we get with observations. And System 5 seems to be way weaker in response to this, to its own North Atlantic oscillation. So, I mean, we know that this assessment is super preliminary. There's many more stuff to test. And this is basically what I did when I went to Leipzig. So from here, like before here, everything is published in a paper that should be accepted soon. From here, everything is quite preliminary. So like take all this with a pinch of salt. But basically what we wanted to do in Leipzig is to assess better how the teleconnections are reproduced. First in our model, also in observations, and also in the different CMIP6 models that we are using for training. And Alma is already raising his eyebrow here. No, but like, and well, we basically what we did is like to build this kind of graph with the different indices and links between these. And this is a use case in South America. Sorry that I didn't mention this. So basically, we took like the most important actors affecting seasonal climate in South America, such as ENSO, the IOD, the stratosphere, the SAM, and so on. We constructed all these different indices and we assembled this graph, and then we compute the regression coefficients between observations, our model and the different CMIP6 models. And now we are trying to understand all these different numbers that we see here. And from a very simple analysis, we could say that our model is effectively learning what we see in CMIP6 models. So this is something that, okay, we can confirm that at least our model is not like producing something that is completely off. Yet we see, we see very different behaviors. So we see the link between the ENSO and the IOD here in red. You see that more or less is in phase everywhere. But here in observations, we see that it's way stronger compared to some models in CMIP6. And our model at the end gets this link, also like this lower like this smaller, like lower link, say. Then if we go to impacts, things get very messy, and this is where we are now. So basically, we are trying to understand how we can digest this information to make it useful. And hopefully the idea is to use this information to filter the simulations that we used for training, if we could, like in some way or another. And then the other set of works or experiments that we conducted in Leipzig to understand better predictability was a set of masking experiments. So basically, we take all the inputs that we use for our models and we mask different regions. So we tell the model, okay, just use information from the Indian Ocean or just from the ENSOR region or the Pacific. So for instance, these are several masks here that we applied to sea surface temperatures. And we did also the same for the stratosphere. So what happens if we remove the stratosphere or not, and what happens if we add information from the atmosphere in the stratopics and so on. And here we can see in a very quick way what happens to the global CRPS. So if we use as a first hint, if we measure the CRPS for the whole globe in predicting temperature for DJF, we see how the predictability increases as we add more and more components, and then we are interested to see how much each component is adding to our final prediction and if it's meaningful or to us or not. So here we can see up until here how much information we get from the oceans, and then what happens is if we add the stratosphere, and then what happens if we add the atmosphere and the stratopics, and this is the final full model. So you could see that ENSO already is like adding a lot of predictability, but still many of the components, they provide also like quite useful information. And here in this map, you can see a point-by-point illustration on which of these masked models or experiments provides a better skill. And this, it's quite interesting because we see that sometimes using the whole information from our simulations is not the most meaningful, meaning that just by using what the simulations use, I don't know, simulate at the ocean level, so just by using information from the oceans, we can get a more reliable estimate of predictability and so on. So we are now trying to explore like what this doesn't really mean, and if we could optimize our final predictions to say, okay, just use the information that we really think is useful from our climate simulations, because maybe some other variables are adding more noise than practical information. Okay, so I think that's more or less it for the ongoing work, and then for the future work. So, well, we would like to improve many aspects of this kind of framework. On the first aspect could be the modeling itself. So using a more powerful generative modeling that is more state of the art. And there is a lot of literature now on score matching, diffusion, flow matching, energy matching, like all these different frameworks that could be leveraged. I'm currently like implementing a version of this setup using diffusion, and we see where it goes with that. Yet we will also like to have an increased spatial resolution. So I didn't mention this, but we are using we have like a 5 degree per 5 degree spatial resolution in our first experiments. If we want to increase the resolution and also use diffusion, this might be a bottleneck because diffusion models are quite inefficient compared to variational autoencoders. So we are exploring other alternatives like latent diffusion, but and so on. And then we would like to test, because everything was trained on climate simulations and test using observations. We wanted to test, we want to keep working on how to fine-tune our model using real observations to see if we get something that is closer to observations and so on. But as I mentioned, we don't have a lot of samples, so this might be very problematic, and it's not easy to find a strategy to really use the little information that we have from observations in a efficient way for the whole model. So it's something we are taking a look with quite soon. And then we want to also try to use more information, so more variables and a better initialization. So I think it was interesting that by just using monthly data and four or five variables that I listed before, we could get these levels of predictability. What happens if we use like more information from different variables and also different layers in the atmosphere and even in the ocean as well. So because now we're using just information from the surface, so this is something we'd like to test. But yeah, this all ongoing work, also trying to improve the framework from the University of Leipzig that I mentioned earlier. So I don't know, if you're interested into any of these topics, please reach back to me. And yeah, so some final conclusions for the talk. We could say that we stably train a generative model using climate model output for predicting seasonal anomalies. This is quite interesting because we thought we didn't have much samples to train these kind of models, and it seems like it's providing something that has some levels of meaningfulness. Temperature predictions show good skill against the climatology and even a very comparable skill against System 5, at least in some areas, not everywhere, of course. For precipitation, we are showing like a way weaker and limited skill, and we cannot claim that we are outperforming System 5, and maybe in some very, very specific regions, but not in a meaningful way. But still, I think with the levels of skill that we get are quite interesting to continue doing research. Yeah, just to say that the generative approach that we use, it's very interesting because of this capability of predicting ensembles in a very computational cheap way, and this is and it seems to provide like a coherent and prediction. So this is also something interesting. And yeah, from our simple teleconnection analysis, we are seeing that we get something that resembles the teleconnection patterns that we see from observations and the different forecast systems like System 5. But I mean, we acknowledge that we need to really push forward this analysis, and it could be interesting also to detect biases on different climate models, even from CMIP. And yeah, that's all. So thank you very much for being here.
Well, thanks a lot. Be biased, but
yeah.
All right. Does anyone have any questions?
Yeah, please.
Like two questions which are actually related. So I'm just gonna start. So in the climate model, when we have different ensemble members, we estimate that each ensemble member and what's the realization internal climate variability. Do you think you can have the same interpretation of your ensemble members? That each ensemble member is a realistic interpretation.
So I think the difference here is like, yeah, that's the good point from using simulations, that each different ensemble, like it's a different realization of climate variability, so you can learn from it as it was like some observations. But when you apply this methodology, you train it on these different simulations, and then you initialize this model with observations. What you are doing is like putting in phase, in a way, this interannual variability to some degree. So then from there, we could say that the ensemble at the end is like in phase and then predicting the future seasons ahead. So yeah, I would not say that now provides independent realizations of the climate variability, because now we have a common initial state prediction phase.
So we initialize them.
Yeah, then it's the same. It's the same as an initialized climate model, but because I would say that simulations from climate projections have independent realizations of climate variability.
Okay, but like if we compare the CS5,
Yeah,
like I don't know how many members, they all represent an estimation of internal climate variability over the length.
yeah. Then I will agree with you in this sense, but I would not say that it's like a completely independent realization of climate.
I'm not saying they're independent.
Okay, because I don't know, I understood that you were saying that they're independent, but then it's analogous to what System 5 is doing. So
you think so every member that you have is realistic?
Yeah.
It's not like just the ensemble mean that.
No. Like, no. And I can show you, I don't have Yeah, but I can show you some nice plots because like if you check the predictions, like the different anomalies, in the, for instance, if you go to a more predictable region like the equator or like the Pacific Ocean, whatever, you see that ensembles are quite similar within each other. So there's like a small spread in the simulations. If you go to Europe, like you can see how you have completely different patterns of variability, and I think because the model it's not able to link like the predictability, not to say okay, this is a pattern that it occurs, and then projects all the variability that sees in CMIP6 simulations into the future. So yeah. Sorry, I thought you were mentioning independent, and then I was confused. Yeah.
Interesting. I don't come from seasonal. I think or whatever. So sorry if what I say, but you say that you'll perform in numerous inland areas. I guess that those are because in the skill plots you say you get the better higher score in overseas.
So I mean, if you compare against the climatology, of course, like overseas and so on, you have more predictability. And then against System 5, if you see all the plots all together and so on, if you see on peak, System 5 wins mainly overseas.
Yeah.
So System 5 has a proper ocean model of the layers and so on. So I think, but then lacks like the capability to project this into land surface areas. I don't know. Like,
where I was gonna go, where I wanted to go. So I guess that because of the what you said at the beginning, like the different systems that hold a little bit of predicting capability over seasonal times are more ocean or land surface or whatever. Do you think maybe that's the way to go into getting more inland predictability to train into variables that go in that direction?
Yeah. I mean, for sure. You mean like land variables and so on? Yeah, for sure it will be like a way forward. The problem is at the end, as you are using climate simulations, you are like tied to how well climate simulations reproduce these land surface feedbacks and so on. So yeah, at the end, the problem is like because you need all this sample size, you need to be coherent on all the training set and the validation and the testing set. So you need all the variables across the different sample like sets. So it limits you a bit in this side. But yeah, it could be a way forward too. Yeah. So one of the experiments that we did, because we are not using soil information, but we use like temperature and precipitation as a proxy of soil information. And we are with these experiments that I show at the end that we remove with the mass and so on the information, we are testing how useful this information is. But for now, it seems like the most useful content information comes from the ocean and the stratosphere probably. And then once you go into the atmosphere, you don't get that much. And once you go to land surface, you really don't get, and it could be even worse. So yeah, I don't have the exact figure. Yeah. Okay. Yeah, please.
Go to the beginning of the presentation. So what from the climate models from CMIP6, which variables do you use to train?
Yeah. So basically, perhaps I went too fast on this. Sorry. For the inputs, we are using temperature, precipitation, SSTs, the geopotential 500 at 500 Pascal and 300 Pascal. And in the last set of experiments that I showed you in Leipzig, we added information from the stratosphere. So we're using the geopotential in this case, although we will prefer to use information like the U component of the wind in the future. And then we use like the previous 6 monthly anomalies for the previous 6 months for all these variables. Yeah. Yeah.
And then training same variables for
exactly the same variables like from CMIPs. It takes
throw in some extra variables in the training that like they're slow that somewhere.
Yeah.
Will it continue the process or just okay?
The idea is that it will try to learn what the simulations have simulated as close as possible. If this information is useful to predict this, like these anomalies in the future, then the model should learn it. If it sees that it's not linked to what he sees in the future, it should be able to discard it. But yeah, I mean, there is a lot of room here because the setup is very simple. So I think there's room for improvement.
I mean, it's kind of tied to the question of how you constrain. So you say there's some issues with I don't know how this works, but
Yeah.
it's difficult to go beyond weather because it's unconsidered quantities that you can get. Is this a part of the problem? So when you
no, like here, no, it's not the case because we do like direct predictions. So we target the entire season ahead. So it's not like we are trying to do a simulation, you know, like a rollout simulation. Yeah, maybe I can explain this better. But basically here, the weather emulators, they try to do what a dynamical simulation like model does. So basically to do the prediction at 3-6 hourly interval. In our case, we are doing like a statistical prediction, but using the CMIP6 information as, you know, so you don't have these stability issues. Yeah, you have many other issues, but not these ones. Yeah. Yeah, please.
On the like, if you have any insight on the models you use, because I thought that it was really cool what you did at the end, like checking with individual models' performance.
Yeah.
Climate. Because I see that you have like kind of similar models, like
MEDOC 6, MEDOC ESL.
Do you have any?
So basically, so basically, when we choose them was a very practical decision. It was like, okay, which models, large ensembles have more than 20 simulations and that we have them available and so on. So this is something that is like what we want to check now. I have also tested some large ensembles now from CSM-lens2 and other ones. The thing is, like, there is a lot of issues and things to take account. So you could check all the teleconnections and then you get all the numbers and you have to try to understand what is going on here. Another thing that could be interesting is to check biases in how they reproduce the force response, because all the different CMIP6 models, they have different biases. And what we did in our setup was we do all this like standardization and all the different models separately, and we remove the trend, and then hopefully we get something, but still, you know, that the physics will be highly unbiased there. And if I show you the original, the raw plot, when you see the different CMIP6 model, you could see all the huge biases across models. So I don't know, I think this is what we would like to explore, like to see how we can filter models, but there are so different dimensions to tackle this problem that it's quite difficult. So maybe one option, we did like a whole global setup, which is like maybe too much, and maybe going targeting a more specific region and then carefully there, as we did here, when more or less the processes are understood, slowly taking a look at the different models and then filter them. Yeah, I don't know, but this is something, quite difficult to do it automatically. This is a research question that it goes across the whole field, no? Like if you want to provide a projection, which one is better, which one to use, which one not to use. Yeah, I don't know.
Do you evaluate the reliability of your forecast?
Yeah, very good question. Like, no, it is something I would love to see, because being a generative prediction, there is some degree of reliability in the CRPS, but if you want to do it more like straightforward, like probably you have to decompose the. So something I would love to do, and also now that I'm working with a completely different generative approach, to see if we see differences in reliability between the two methods and the dynamical model. But yeah, it's something I will love to see, like, and check in the future, short term. Yeah. Yeah, I think it's Pep. At least I saw Pep. I don't know if anyone else. But we don't hear you, Pep.
Yeah, can you hear me now?
Yeah, we can hear you.
Okay, just one quick question. When you just predict the like the variability with your model, then you add that to the CMIP6 ensemble mean?
No, I add this to the lowest regression. So basically,
Okay, so you just extrapolate from.
yeah, it's like a retroactive lowest regression that I thought it was the best thing estimate.
Okay.
Yeah. Do you think adding this to the CMIP6 ensemble mean could be better in this case?
I don't know. I was gonna ask, maybe you can. I mean, it's just a matter of adding it and computing the skills scores, right?
Yeah.
So maybe you could try.
Yeah, I could try, definitely. Yeah. Yeah, I don't remember the reason exactly why I didn't try at the beginning. Probably because I was seeing some biases still in the trends, and then I thought, okay, maybe I could
Yeah,
just,
probably there will be biases, so I don't know if it's the best.
yeah. So, yeah. But it's a good point. Thank you, Pep.
We have time for one more question.
I
No,
will.
takes time.
Yeah, please.
There is some literature about that for some variables, seasonal, and other predictions are gained skill by getting larger and larger and larger ensemble.
Yeah.
I wonder, have you checked if the skill, how your skill changes with the ensemble size?
Yeah, I have not done it like globally. Like I very quickly stick like to a 150 setup, and because I did some tests in Europe already where the variability was larger, and it really quick converges. Like if you see here ACC to the median, it converges very quickly to the 23 samples. Perhaps like doing this on the mean of the temperature is not the best.
It'd be nice to do this on video.
On linear or like on extremes as well, on the tails of the distributions. Like, yeah, I think this is also something quite interesting to see and do it maybe globally. So it is true that when I see the literature, many papers claim more predictability from larger ensembles, but also you have to be sure that your system, either statistical or dynamical, produces proper ensembles, because if it produces more of the same thing, then maybe it's the case for here, and then maybe it's the reason why we converge very quickly on XCR. But it could be interesting to see this kind of sample spread plot. Yeah, I agree with this. Yeah. Okay.
Right. Lluís, again.
Yeah, thank you for the people online. Ciao.